we'll go ahead and get started. Do want to thank everybody for spending some time this afternoon to join us and see how Maser Consulting utilizes the Amberg trolley system to provide surveying solutions to our rail clients. So Maser Consulting provides lots of different surveying solutions for the rail industry. We use conventional surveying methods. We use the Amberg system. We have a high-rail mobile LiDAR mapping system and an aerial platform. But today we're going to focus solely on the Amberg GRP 1000, 5000 trolley systems. What are they? These are our workhorses. This is the GRP 1000 on the left-hand side. It's the basic model. We use this for our geometry measuring solutions. We get with the total station, we get better than a 2 millimeter horizontal vertical track position, typically better than a 1 millimeter super elevation or cross level measurement. The gauge is normally 0.5 millimeter or better. And we have the ability to use this with a total station for positioning. We can use it with a GPS system. We can use it for just a straight odometer for random type of stationing or for client-derived stationing. On the right-hand side is the GRP 5000. This one's outfitted with the 6012 scanner made by ZNF. It's the same trolley frame as the 1000 with the addition of a battery column and a scanner. This particular scanner gives us almost a 360-degree field of sight, which means we get the ceiling, the walls, the trough inside between the tracks, the rail heads. We have one little spot there we can see on the far right-hand side where the two-wheel portion is, that the rail actually gets blocked out by the trolley, but is very, very minute. In this, we get about 5 millimeter data resolution inside our scans. It is rotating somewhere around 200 hertz. So we're getting about 1 million points per measurement as it goes on per second. Again, this one's also capable to work in a 3D mode with the total station. We can use it with the GPS, with an odometer. We're also working on vetting out an IMU system to help us increase our productivity. We're in the process now of working with that in the GPS and a instrument setup that will really enhance our capabilities and give us a little more flexibility. So how does this all work? How does it all start? Like every other project, it starts off with good control or good foundation. We like to take a look at the tunnel we're working in or the rail corridor we're working in, and we plan out our work. We take a look at curvature and tangents and where does it make the most sense to set our control points as we go through. Control points, once we figure out where we want to put them, are embedded in the walls or in the tunnel or some solid foundations along the rail out there on the wayside. We use primarily the adapters that are shown on the right-hand side. It's a Goecki insert. We actually drill those into the concrete. It's a flush mount type of system, which is very, very nice, which means there's no protruding bolt studs. Back in the time, people used to drill in epoxy and 5/8 bolts into the walls and screw the prisms to them, and the flagmen or watchmen or inspectors later on would be walking through the tunnel and catch their shoulder on top of these studs. And so with the inserts now, we're completely flush. It gives us a nice ability to rotate the prisms so we can see them from either direction. So we'll go through and set the prisms. We do a traverse and balance out our control survey. And this gives us the ability to use these prisms not only for the initial survey, but we also use them for the construction and the post-construction as-built work we do. By doing that, we get really solid repeatability of data. And when we're comparing information, most of our project specifications for the contractors we work with are 1/8 of an inch or better. And so we have to have repeatability of data to be able to ensure our client that the contractor has built the track inside of those tolerances. So these are two of our current projects we're working on. The left-hand side is the B&P tunnel in Baltimore. It's an Amtrak tunnel, and the right hand is an image of the Whirlpool Bridge going across Niagara Falls. Incidentally, it's also a Whirlpool or also an Amtrak facility or structure. The BMP tunnel project was a 55-hour outage. We actually used the trolley to measure existing track conditions, process the data in the field, sometimes right in the tunnel, and perform a alignment regression on site. Use the smooth alignment to lay out new track for direct fixation, and then work with the contractors to get it laid out, get it built, and then do a post-construction measurement on it and do a deviation report. So a lot of things happening in 55 hours. And this gives the ability for the client owner railroad to take the track out of service on a Friday and return it back to service again on Monday. So really fast-paced, and the trolley makes that possible. The other project is the Niagara Falls project. It was a precondition type of survey. We laid out the track center line, and then on a nice balmy sunny day, we did the as-built here at the very end. So it was a little chilly on that one. So what do we get when we do the measurements? This is what we call our inner geometry. After we process the data, we can take a look and see what's happening between the railheads, which we like to call inner geometry. So I can get project stationing, super elevation, curvature, twist, and gauge. This particular job was one in Canada we did, so the units are in meters, but it's convertible back and forth. This is the outer geometry, and this we have our track stationing. This is like the plan view looking down on the project itself. So now we're seeing the wayside and seeing the survey points as we measure them. We have the odometer stationing, the XYZ position. We have the curvature and the gauge of the track itself. Typically I need to back up one I skipped already ahead. Apologize. In this type of measurement, the density of the data is derived by how fast the trolley operator walks. So if the trolley operator walks slower, the total station is updating the position with the trolley as it goes along, and feeds the trolley the coordinate values. The pace of the trolley, then, there may be as many as 3 to 5 to 7 data points per foot. So we're able to really get dense data inside our measurements. And then when we process the data, we're able to extrapolate it out and produce it in we'll call it a user-defined stationing. This particular job, they wanted to station it every 10 feet. So we're able to start writing our stations out at 10. They wanted to know where the point of switch was, so we can make a special note where the point of switch is. But the rest of the stationing follows a pretty close 10-foot increment. And in this, we get track easting, track northing, track height, azimuth, some super elevation, gauge, radius, and then the rates of change. We'll produce this data. We can write it out in an ASCII format, an Excel format, land XML, and DXF formats, whichever the client specifies or likes, or all of the above. And then the client will actually take this and use this for data regression or for as-built information or whatever they like to take a look and see what the track geometry is. We also have the ability to write out individual rails. So this is track center line, but we can also write left rail and right rail out. Once a project's built, the question comes up, how close did the contractor build the project to our design alignment? And we can actually set the construction tolerances in our software from the specifications, whether or not it's 1/8 of an inch, on the alignment or better. And then we get a report by station where it takes the measured survey that we perform on it, compares the measured track data versus the design alignment, and then gives us with a deviation report. And so in this column, we can see where the position has deviated. Starts off at 800 and then goes to 0.27 feet, so almost just over 3 inches. Particular job, there's a reason for this, because the track couldn't get back where the design was due to outside obstructions. Here, the height, again, it shows the deviation in the heights. We get a super elevation, so they had a good super elevation on the track, no cross level. The gauge is a few spots where it's a little wide, just over 1/8 of an inch, and the rates of change, again, show up here as the pink cells. This type of data we can export out in an ASCII format or an Excel format and deliver that to the client. Our next trolley system is the GRP 5000, and we use this to do clearance measurements. And we can take and build the clearance envelope inside our software, and we'll run this scanner. It is track-based scanner through the tunnel and collects scan data as we walk the trolley through. So we get existing track conditions, real-time clearance analysis, post-construction, and we can do, again, client-specific reporting. So how does this work? Is we have here is the trolley, the cartoon of the trolley, the scanner on it, and as the scanner cuts around, it is scanning and collecting thousands of points of data per second, million points per second. And we're able to produce this data and process it into imagery like we have here on the right-hand side. So we can take a look at, we get 360-degree field of sight like we talked about earlier at 1 million points per second. And our data is within 5 millimeters of track center. So our buddy here, our flagman who's sleeping here on the right-hand side, we can actually zoom in on him and see within 5 millimeters how far he is off the track. So we use this type of imagery to walk through. This is one of the projects we did for CSX in Georgia. And this is just a brief video of how the trolley walks through the tunnel as we're collecting data. And I'll play this real quick for you. Pretty straightforward. This is a job we did for CSX where they actually went in, did ballast remediation, took the ballast out of the track, out of the tunnel, lowered the track and the ties, reflooded the track, and then we did as-builts at the very end of the job to make sure that they had increased their clearance. They had problems with the double stack cars scuffing the ceiling inside the tunnel, and they wanted to remove as much ballast as they could and still get a solid rail bed, and then see how much they'd actually gained through the work they did. So after we scan the tunnel, what do we get? So this is a view of the scan data in a profile view. We're able to take the data and cut profiles from our map view, from our scan data. We can cut profiles at 1 foot increments, 10 foot increments, whatever the client specifies. Here we've done as tight as half a foot increments up to 10 footers, 15 footers. So we look at the data and in the profile view, and here on the left-hand side, we see this is the car bodies we've built. And these are some pretty basic car bodies. This are I forget where this particular job was, up in Chicago. Sorry, this job was up in Chicago. So the car body is kind of blocky, kind of chunky. It has about 15 points per side of the car body. We're doing some others that are using up to 30 and 40 elements to make up the car envelope shape. So as we take a look at the profile, here we see there's some type of obstruction inside of our clearance envelope. So we're not quite sure what it is. So we want to ensure to our client that there's not something in here that is going to cause a problem, a piece of conduit. And this one's pretty obvious what it is. But if it was a nodule or something else, we want to be able to see and ensure the client that it's not an issue or something that needs to be removed. So the nice thing about the Amberg software is we have the ability to take a look at the map view and the profile views at the same time. And they are synchronized together by stationing. So in the map view, we can type in the map views here on the right-hand side, we can type in a stationing and use our cursor at the stationing and also see the map view profile on the left-hand side, and then put our cursor on this particular thing here. We can see is a total station. So I can click this, and when I click it, this very thin cut comes out, and I see that absolutely there's the legs of the total station, the tripod, and here's the head of the tripod. So we're able to then cut. This particular cut was at 0 plus 39, so probably 0 plus 40 was our station. And when we cut our stations, we like to cut them in 10-foot swaths. So we make this particular cut would have been at 0 plus 40, but we look at the data from 0 plus 35 to 0 plus 45, and that scan width of 10 feet gets condensed into one profile. And we do that to ensure that nothing is missed in that 10-foot swath. So if we just cut our profile at 0 plus 40, an element or an item could be hanging down inside the tunnel, or a light fixture could be encroaching in the clearance envelope at 0 plus 36, and we wouldn't see it. So we use the 10-foot, 5-foot ahead and 5-foot back, condense it down together, and then take a look at that particular profile cut. So we're able to work inside that cut to get the data that we need, and also take a look and make sure we have it clean. So in this particular case, if we were going to cut this profile and wanted it clean, I would cut it at 0 plus 37 with a 1-foot bandwidth, because I know that everywhere else I'm good, but I have this obstruction at 0 plus 40 that I don't want to see in my profile. So our next slide is from one of our projects, and this is about 1,200 feet of track data, and these are cut at 10-foot increments. And we've put together just a little video clip of the PDF slides. So you can see the dynamic shape of the car body. And the dynamic shape is as a car goes around a curve, the end excess and center excess expand on the car, because if you were a kid and you had Lionel trains, when you ran your train around the curve, if the tunnel was too close to the curve, the train always hit the curve or always hit the tunnel. And that's the end excess of the car. Same thing in a subway tunnel is as the car goes around a curve, you have center excess and end excess, and that causes the shape to expand from what we're looking at now as a tangent shape to a more almost like a loaf of bread. And so it grows to the sides and to the middle. And so we have to account for that as we do our profile checks. So in this, I'll run the slide and pay attention up here to the upper right-hand side, and you'll watch it grow. The green numbers here indicate we have good clearance. The numbers across the top and across the side are the clearance from the tunnel wall here in the benches over to the shape of the envelope. So I'll run this slide for you real quick. You can see a few reds grow. And here we have a conduit. And it settles back down. In this last image here, there is a bank of conduits running through the side right here. Now this envelope has a lot of extra clearance in it, so there's some grace in this one. So even though it shows red here, in the analysis later with actual car body through the client said, no, we don't have a problem here. So we like to go through and we'll present these to the client. These are cut every 10 feet, depending on what the client's looking for, and we'll produce these to them. We can also write these out in DXF formats and deliver those in a 2-dimensional, 3-dimensional to use in a CAD environment. So when we process our data, again, we can do it by specific increment, specified station. The bandwidth we define, again, is at that 10 foot. Our outputs in DXF, PTS files or PDF files. The PTS files, we can actually write out the whole cloud of the tunnel walls and deliver that to a client who can view that in a 3D viewing software like Cyclone or Topodot. They want to do some different analysis on what's actually happening inside the tunnel. Some of our clients ask us to use a software to and use Bluebeam or Editor to show them what's actually in the profile. So here we can see the traction power down at the bottom here, the heads and the cover board for traction power. There's different pieces of conduit hanging out across the top. Here's the walkway and utility bench, and again the dynamic envelope of the vehicle. So we're able to see lots of different data points on this. With that, that's my presentation. I hope Maria is on board. She is our facilitator. I hope that some folks have sent some questions in, and be more than happy to answer these questions. If you have real specific information or you would like to dig a little bit deeper into the presentation to talk more about it in depth, you can reach out through the address here and get in touch, or you can reach out to me directly.
Thank you, Tom. Yes, we do have a couple questions. The question that we have here is from Matt, and he asked, what is the production rate? How much can be done in a day?
The production rate actually varies depending on by the type of survey we do. Using a GPS application for freight, we're able to do miles in a day. I think that we did a job in Las Vegas that I think we did 5 or 6 miles in a day using that solution. If we're in a tunnel environment where the control is and the product needs to be very tight, 1/8 of an inch tolerance, then we can typically do somewhere in the 600 to 900 feet an hour, depending on the type of track. And if the track's curved or if it's tangent track, our line of sight between the total station and the trolley itself.
Okay, thank you. Another question here is from Gio. When using the Amberg trolley and software for maintenance purposes on existing track within curves using traveling cords for horizontal alignment checks, does the software compare the existing to the theoretical design, or does it only relative to the existing track? Sorry, that was a long one. Did you get that one okay?
Yeah, can you run it by me one more time?
Yeah, I'm sorry, it's a long one. When using the Amberg trolley and software for maintenance purposes on existing track within curves using traveling cords for horizontal alignment checks, does the software compare the existing to the theoretical design, or is it only relative to the existing track?
If we are comparing to a design, then we will actually build a design data set in the software. And the design data set is the horizontal track position, alignment, the profile, super elevation, and all the geometric features of that particular track. As we are measuring then in an as-built situation, it is a moving chord, and in a slab track report, the rate of change that we measure is the actual rate of change in that 31 or 62 foot cord, long or short cord, and then that gets compared against the allowable rate of change in the design data set per the specifications. So I hope that answers your question, Matt. Yeah, if not, you can reach out to me specifically.
Yes, definitely. And I do have Gio's email here. So yes, we could always follow up. Another question here is from Kevin. Can you introduce 3D models into your Amberg software?
3D models. Scan. I'm not sure if he's asking about scan data. Yeah, I'm not sure. That's a pretty broad term.
Okay. All right. Again, we could follow up with that one. And let's do another one here. This is from Sharon. Will it shunt the rails and cause an EOT warning?
That's an equipment on track warning, and no, the way Amberg has built the trolley, it uses 2 different types of wheels. Ones are PEC plastic wheels that will not shunt, and the steel wheels that we use for a more precise measurement. The bearings of those are actually insulated, and so the trolley will not shunt the rails and show an EOT. So we do use it on live track a lot.
Okay. Another question. This is a quick question from Glenn. Is it heavy? I guess he's asking, is the equipment heavy? Is the Amberg heavy?
The trolley itself, the frame, is about 40 to 45 pounds. In the GRP 1000 setup, it's pretty easy for one person to pick it up and move it. When you add the battery column and the scanner, it does increase the weight to probably maybe 125 pounds, which is it's more awkward than anything else. One person can pick it up if you had to in a hurry. Typically, once we have the scanner on and the battery column, we try and get some help to make that happen. The nice thing about the trolley is we're able to get it on and off the tracks in just a matter of seconds. So unlike a high rail vehicle where you have to have a grade crossing to get the vehicle on, the trolley is literally pick it up, set it down, lock it in, take your measurement, and if we need to clear up for a train, it's light enough that we can pick it up and put it off to the side, let the train pass, and then go back to our work.
Okay, thank you. Actually, I think that's it with the Q&A session here. So Tom, I guess just go back to you for any final comments and remarks.
Just like to thank everybody for joining. I do know that we have some other sessions coming up. I think one is on substations here next week. So I invite everybody to please come out and enjoy that. Again, if there's more questions, you can send them to the survey webinars address. You could also, more Amberg specific things, you can send to me, TREED@maserconsulting.com, and be more than happy to get more down in the weeds with you on the Amberg trolley system. Thank you very much.
Thank you so much, Tom. Thank you, everybody. Have a great day.